All right, let's dive right in. Today, we're going to go on a pretty amazing journey, a journey inside the microscope. We're going to explore the super clever ways scientists have figured out how to see things that are basically invisible. I'm talking about the transparent, complex machinery that keeps a single living cell ticking. It kind of sounds like a riddle, doesn't it? How do you see something that's invisible? Well, this very question, this fundamental challenge, is what has been pushing microscopy forward for almost 100 years, and it's led to some truly brilliant inventions. You know, for a biologist, this isn't some philosophical riddle. It's a problem they face every single day. You can zoom in on a living cell as much as you want, but if all its most important bits and pieces are see-through, you're not going to see much of anything. They just don't absorb light, so you get zero contrast. It's kind of like trying to spot a perfectly clear piece of glass in a glass of water. Good luck with that. So let's start there. Let's call it the invisibility problem. We've got to understand what's actually happening to the light that makes these things so darn hard to see in the first place. Okay, so here's the science behind it. When a beam of light passes through a transparent part of a cell, it actually slows down, just a tiny, tiny bit. This makes the light waves fall a little out of sync with the light that just went around the cell. This is what's known as a phase shift. Now here's the catch. Our eyes can't see phase shifts. We can see changes in brightness, we can see color, but phase shifts are totally invisible to us. The information is there, we just can't access it. So, how in the world do you solve a problem like that? Well, this brings us to our very first brilliant solution: figuring out a way to actually use those invisible phase shifts and turn them into something we can see. And this quote from our source material really just nails it. Without special arrangements, phase changes are invisible. Yet often these changes in phase carry important information. It's all about unlocking that hidden information. And the guy who figured out how to do it was a Dutch physicist named Frits Zernike. Back in 1938, he built the very first phase contrast microscope. I mean, this thing was so revolutionary that the Zeiss company started making them during World War II, and Zernike eventually won the Nobel Prize for it in 1953. So yeah, it was a pretty big deal. So how does this magic trick work? Well, it's a really clever two-part system for manipulating light. First, a special ring shapes the light before it even hits the cell. Then, after the light passes through the cell, a second special ring does something amazing. It slows down the background light, just enough so that it falls back in sync with the light that got slowed down by the cell. And by doing that, bam, it converts those invisible phase shifts into visible differences in brightness. All of a sudden, the hidden structures of the cell just pop right into view. And let me tell you, this was an absolute game changer. For the very first time, scientists could watch living cells completely unstained in real time. You could suddenly see all these incredible details in single-celled organisms, watch processes happening live. And the images you can get are just shockingly high quality for what is really a pretty simple setup. Okay, so phase contrast is fantastic for seeing the overall layout of a cell, but it can't tell you what you're looking at. What if you need to find one specific kind of molecule in a sea of thousands of others? Well, that requires a whole new approach, a whole new solution, making the molecules glow. And that's the next huge problem to solve. A cell is an unbelievably crowded place. So how do you track just one single protein in that chaos? The solution is, well, it's as elegant as it is powerful. You attach a tiny little molecular light bulb to it. This technique is called fluorescence microscopy, and here's how it works. First, you tag the molecule you care about, say a specific protein, with a special fluorescent stain called a fluorophore. Then you blast the entire sample with one color of light, let's say blue. Now that fluorophore, it absorbs the blue light, gets all excited, and then emits its own light, but at a different color, like green. And here's the final trick. The microscope has a filter that blocks all the original blue light, so the only thing that makes it to your eye is the green glow coming directly from the molecules you tagged. The huge advantage here is specificity. I mean, it is incredibly precise. You can pinpoint the exact location of molecules inside a cell. But, and this is a big but, it's got some serious downsides. The glow can actually fade over time, which is called photobleaching. And even worse, the high-energy light you need to make them glow can actually damage or even kill a living cell. That problem is called phototoxicity. So we solved the problem of specificity, but that created a new problem: blur. All that glowing light just creates a fuzzy haze. To fix that, we needed to find a way to get an even sharper, deeper look. See, here's the thing. When you light up a fluorescent sample, you're not just exciting the single, thin layer that you're focused on. You're also lighting up all the stuff above it and below it. And all that extra, out-of-focus glowing just creates this blurry haze that can totally wash out the details in your image. So the new question is, how do you get rid of the blur and get a perfectly crisp picture? The answer is the confocal microscope. And the key innovation here, thought up by Marvin Minsky way back in the 1950s, is a tiny little pinhole placed right in front of the camera. This pinhole acts like a bouncer at an exclusive club. It only lets the sharp, perfectly in-focus light through while physically blocking all that blurry, out-of-focus light from ever reaching the detector. It's just brilliant. The result is absolutely dramatic. It completely wipes out that background haze, giving you incredibly sharp images. And because you can scan this pinhole layer by layer through the sample, you can create these optical sections without ever having to physically slice up your specimen. Then you can stack all those digital slices together to build these just stunning 3D models of entire cells and tissues. It's used everywhere now, from medical diagnostics to making sure pharmaceuticals are up to snuff. So, after looking at these three pretty incredible solutions, what's the big takeaway? Well, it all boils down to picking the right tool for the right job. Let's just quickly recap the toolkit we've been talking about. If you want to look at live, transparent cells in their natural state, phase contrast is your go-to. If you need to hunt down very specific molecules, you're going to use fluorescence, but you have to be careful not to harm the cells. And if you need the absolute sharpest, high-res 3D images possible, you bring out the big gun, the confocal microscope, even if it is a bit slower and more complex. And really, that's the most important point. There is no single best microscope. It just doesn't exist. Each one of these is a highly specialized tool, a unique solution to a very specific problem of invisibility. The right tool depends completely and totally on the scientific question that you're trying to answer. Which leaves us with one final, pretty amazing thought. For almost all of human history, what was going on inside a cell was a total mystery. But now, thanks to these technologies, we can watch the machinery of life in action, in stunning, dynamic detail. The only question left is, what are we going to discover next?